Okay. Okay. So welcome. So we will continue our study of entropy quantities for quantum states. So last time we were looking at this, the triangle inequality for entropy, also called the Araki-Lev inequality, which is this, that the entropy of AB under a joint state rho AB is greater than or equal to HA minus HB, take the absolute value. So it's greater than or equal to HA minus HB or HB minus HA, whichever is called. Okay. And we saw an illustration of this when the state rho AB, the joint state is pure. So this is the state vector ket rho AB. And we saw this triangle inequality in this special case when the joint state is pure. And on the way, we found out a very nice algebraic way of writing down joint pure states or entangled vectors. So that was the Schmidt decomposition. This is the Schmidt decomposition, the proof of that. And then finally, this is the statement of the Schmidt decomposition. So this is my entangled vector over the system AB. Okay, but it turns out that you can write it like this. Okay, so in this decomposition, the first vector is an eigenbasis for the density matrix rho A, and the second vectors W are an eigenbasis of the density matrix rho B. So rho AB is pure, but in general, the reduced density matrices rho A and rho B are mixed; they are impure, and we get some non-trivial eigenbases and non-trivial eigenvalues. So the eigenvalues are this lambda A, and in this expression, square root lambda A comes out here. Okay. So what is very interesting and exciting about this is that there is a bijection between the eigenvectors of rho A and the eigenvectors of rho B. So they are matrices on different systems. So in particular, these vectors have nothing to do with each other. Yet there is this bijection between them, which arises because, I mean, they come together to form this pure state rho AB. So that forces a bijection between the eigenbases of rho A and eigenbases of rho B. And you can see that the eigenvalues are the same. Eigenvectors in general are different, but the eigenvalue is the same. It is the same lambda. So what have we seen from this study? That rho AB was pure, so the entropy is zero. But we have seen that the entropy of A, okay, it will be the entropy of this vector of eigenvalues. In general, it will be strictly positive. But entropy of A, nevertheless, is equal to entropy of B, simply because they're the same eigenvalues. Okay? And then the difference becomes zero, and the Araki-Lev inequality is saturated. So this is what we did last time. So today we will continue with our study. So let's start up with a fresh page. Yeah. Yeah. Okay. Yeah. So let's start the page. So by the way, do you know? Well, actually, I can find it out myself. What is the academic timetable? So courses get over by end of December or something?
I'm not sure, but I think the grades have to be uploaded by January mid.
Grades have to upload. But you are not taking this for credit, are you?
Yeah, yeah, I'm.
You are taking this for credit.
Yeah,
So, but then you should send in the answer to that assignment.
yeah, I will do that.
Yeah, yeah. So it's something. Then I will quickly give you an assignment on this quantum part also. So at least one on classical, one on quantum. Okay. I mean, the quantum one will be easier because, of course, I mean, the subject is more difficult. It's totally new, and also, I mean, we will be covering less material in the quantum part. But at least, okay. So if I have to upload the grades middle of January, so basically the course will wind up by end of December. And I think I'll send the assignment uh, like very end of December or immediately in early January, possibly by very end of December. But you should meanwhile sending the answer to the yeah, possibly.
First one, yeah.
Yeah. I thought you're not taking this for credit, that's why I didn't bother you about that. Okay. Anyway, are you doing any other courses this time?
No, no.
No. Then you should have sent it in.
Yeah, I'll
Okay.
send
So
it.
anyway, let's go ahead. And as I said, ask me for hints. Okay. Or ask around. I mean, so these things, I don't know. I mean, these things, this is a 400 level course, so the assignment will probably be a little more difficult than what you may have seen otherwise. So really, I mean, the assignments will make you think in ways that you will encounter in the course of the research later on. Anyway, so let's start. Yep. So we will see the proof of the Arakiliev inequality today, but on the way we will see many more things. So let's continue, and we'll come back to Arakiliev or triangle inequality in due course. Okay. So yeah. So I define what is the entropy. There. Okay. And I also, I think, had defined what is relative entropy. So let me write it down. So the Shannon relative entropy. So take rho A and take another density matrix sigma A on the same Hilbert space A. So this was defined to be. So, oh, sorry. What am I writing? I only wrote half the definition. Relative. So this is the correct definition. Yeah. Yeah. So trace of rho log rho minus trace of rho log sigma. Okay. I just collected up and written it in this nice form. So this is actually the classical definition only. So let's spend a minute and see that. So in the classical world, in our language, classical probability distribution of the diagonal density matrices. So rho will be summation over I, Pi, and then in our Cadbra rotation. So as well. So and sigma will be the same thing, some Qi, but diagonal density matrix. So Cadbra will be. And now, uh, so the right hand side is just telling us. So this is trace. So you can see rho will be like P1 to Pn, let us say, and then log of this. So remember, we had defined how to come up with functions for the Hermitian matrices. So go to the eigenbasis and apply the function to the eigenvalues. Okay, so you get a new operator, so which is the same eigenbasis before, but the eigenvalues are changed. Okay, so that's how I defined log of a Hermitian matrix. Okay, so this is the log of a density matrix. So this is log P1 log Pn, and this is log P1 So now, I mean, all these are diagonal matrices. So you can see that this easily evaluates to what the expression that we have seen earlier in the classical half of the course. So it is summation pi log pi minus log qi, right? And this is log pi minus log qi. I can further compress and write log of pi. So I hope this is clear, that this is indeed a generalization of the classical definition.
Yeah.
Is this clear now? At
Yes.
least, yeah. So, of course, the quantum catch here is that in general, rho and sigma are not diagonal in the same basis. Okay, so they don't have a common eigenvalue. If they had, then I mean, you could have just done the same calculation with common eigenvalue. In general, they are not diagonal in the same basis, but nevertheless, as operators, log rho is well defined, log sigma is well defined. Just as the difference of two matrices. Okay, and then rho is also another matrix. So we're just multiplying two matrices out here and take matrix. So yeah, but you can see that for general matrices, the definition, I mean, is a little complicated, but at least, I mean, it makes sense mathematically. And let us say the matrices were given explicitly to you, you can evaluate this quantity on a computer. Okay, so let us look at some properties of this. And I'll first of all try to convince you that these properties are exactly the analogues of the classical properties. Okay. So one thing is D is breaking equal to 0. So equal to 0 if and only if rho equal to sigma. This is less than infinity. I mean, so remember this D quantity can be infinite also. Already classically you've seen it. So there is analog of. So this is less than infinity if and only if support is contained inside support sigma. Okay. So two basic properties. Let's try to prove that. Right. Okay. So let us see what this d rho sigma is in a little more detail. So rho, I'm expressing it in the eigenbasis of rho only. So it will look like P1 to some Pi. Of course, log rho also evaluate in the same eigenbasis. Log P1 to log Pi. Now let us try to evaluate log sigma. Okay. So sigma, of course, has a different eigenbasis as compared to rho, but I'm going to do a change of basis and write down the operators log sigma in terms of the eigenbasis of rho. So this will make it easier to evaluate this quantity, at least prove this inequality right now. So let's see. So let me write sigma. So this is where Cadbra notation helps me. So this is This is, we know, summation over, let's say, J, then Qj, and let us call this Wj. So this is in the eigenbasis. And now so log sigma. So now I'm going to convert to the eigenbasis of rho. So let's give the names to the eigenbasis. So this is V1 to Vn. So these are the eigenbasis for rho. W's are the eigenbasis for sigma. So this will be summation J log Qj. So now Kebra Wj. So this is summation I prime. So let me see if I can write the expression directly. So this will be the J I, this will be I prime Wj, and this will be so Vi, Vi. Okay. So does this make sense? So Wj, I'm going to write it as a linear combination of Vi's. And because there's inner product structure, like if I write Wj as a linear combination of Vi's, the coefficient, the complex coefficient multiplying the vector ket Vi is this, given by this inner product. Similarly, the complex coefficient multiplying Vi prime, okay, the vector ket Vi prime is given by the complex conjugate of this, but the order has been reversed because this is coming from the bra Wj out. Okay, and this is ket Vi bra Vi. Is this clear?
Yeah, okay.
Yeah. Okay. So this is what I have. So let's keep it this way. Okay. So let me next page. Okay. Good. So log sigma, I'm writing it in the eigenbasis of rho only. So this will be just write this coordinate. So this will be sum over J log Qj and multiplied by Wj is V1 and V1 W. I'm just writing the 1 entry. Okay. So this is the entry for V1. And then there'll be entries here, 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 everywhere. Okay. But I just want to give you an idea of the 1 entry. How does it look like? Okay. So this is the entry 1. Okay. Now I'm going to do log rho minus log sigma. Okay. So you can write down what the expression looks like, and then I'm going to multiply it by rho and then take trace. So what does this boil down to? Trace rho log rho minus log sigma. So remember, finally, when I'm going to take the trace, it is the sum of the diagonal entries of the matrix. Okay. So sure. I mean, I have actually written down the entire matrix log sigma. Okay. I mean, this is the pictorial way, but this is the algebra. And then, so actually, I mean, I have an expression for the entire matrix log rho minus log sigma. Then multiplying by rho is easy because it's a diagonal matrix in our choice of basis. So I have, in principle, the entire expression for the matrix rho times log rho minus log sigma. And so I can write down the trace. But anyway, I'm only bothered about the diagonal elements because I'm going to take the trace. So let me write down what the diagonal elements are. So this will be summation over I. And then the ith element is sum over j log, sorry, no, take some space. So this is sum over I. So pi, pi minus. So this will be so let's write pi, but then I have to write summation over j log qj. The same expression that I wrote for the one, so I can write it for the II element. So as you can see, this is wj vi absolute value square, right? So this is wj v1 and this was v1 wj. So they are complex conjugates of each other, and I get this absolute value of the complex number square. Okay, close the bracket. So this is the expression. So the expression doesn't look so bad. So clear so far?
Yeah.
Yeah. So this is what I've got. And this is what we are going to evaluate and prove the two properties. Okay. Now, so D. Okay. So my D is this quantity. So let's see. So let us prove that this is always non-negative. So now note. So let's fix a I. Now look at these quantities. Mod Wj Vi. I mean the inner product between Wj Vi mod. Okay, remember Vi was a unit length vector. So if I sum these quantities over j, I'll get 1. In other words, these numbers, so after taking mod square, they're positive real numbers. So these positive real numbers add up to 1. I mean, it's nothing but the length of the vector Vi, which is 1. So this can be thought of as a probability distribution, just this part. Okay, so this one, so that's the key idea. This one is a probability distribution. Yeah. So because there's a probability distribution, I can use the concavity of the logarithm. Okay, and then I can write down something interesting. Okay. And put an inequality here. Let's see which inequality. Okay, so this is pi. So let us say, so this is average of logarithms is less than logarithm of average. And then there's a minus sign here, so it becomes a greater. So this is greater than log of average. So summation j. So qj. So is this clear? This was an application of concavity of the logarithm. And let us write this. Pi log pi minus pi. Okay. So let us understand what this quantity is. Okay. So for that, let us come back out here. Okay. So look at this expression that I written for log sigma, but let us pretend now that I did not put the log. So I'm just writing sigma only. So sigma is summation j qj cat bra wj. Okay. So same thing I'm writing, summation j qj cat bra wj. And now I'm expressing wj in terms of v1, v2, vn. So this is the expression. Okay. And I'm still sticking the qj out. So I can write a similar expression for sigma that looks like this, summation over j qj, not log qj, but just qj times exactly this expression, sum over I primes and blah blah. Okay. So so, so suppose I now look at the ith entry. So this expression, okay, the this expression for sigma, the expression without the log, just keeping the qj's. This is the expression for the matrix sigma in the eigenbasis of a row. Okay, in the basis v1, v2, vn. And this is the I prime entry of that matrix. Okay, the matrix for sigma, the I prime entry is given by this complicated Ewing expression. So the ith entry, I now know what it is. It is summation over j, qj, and this is absolute value of wj, vi square. So, and that is actually this expression that I've got here. So basically, this little explanation was to claim that this is a well-known quantity. This is actually equal to the ith entry of sigma in v1 vn basis. Is this clear?
Yes.
Yeah. So I'll call it sigma ii. Okay. Remember, I mean, the I index here is always running over the basis v1. Okay. But note that, I mean, sigma was a trace one matrix. So the trace will be one irrespective of what basis I write sigma in. So in other words, even if I write sigma, the matrix sigma in the v1 to vn basis, the sum of its diagonal entries, that means the sum of the sigma ii's will still be one. So this n tuple of numbers, sigma 1 1, sigma 2 2, dot dot sigma ii, sigma nn, this also is a probability vector. Okay. So, but now what is this expression? This expression is the classical relative entropy between the probability distribution P1 to Pn and the probability distribution sigma 1 1, sigma 2 2, dot dot sigma n. This is nothing but d of, so let me write, the probability distribution Pi with respect to the probability distribution sigma I, just the classical. And now we can invoke all that we know about classical relative entropy. So, so first of all, I immediately get that this is greater than or equal to 0. Okay. And I also get that this is equal to 0. Let us see what is the condition, if and only if. Okay. So note that there were two inequalities in this entire derivation. So there was an inequality here and there was an inequality here. Okay. So the first inequality we can easily understand when it becomes an equality. So one condition I'll get is that PII is equal to sigma II for all I. The two probability distributions are the same. But that only makes this inequality into equality. What about this guy? Okay. So remember, this inequality came by applying Jensen to the logarithm, the concavity of the logarithm, which was here. Okay. So the original expression for the quantum relative entropy of rho with respect to sigma was exactly this. And then I use concavity of logarithms, so I pull the log outside and push the summation inside and got this. So this greater than equal to is coming from here. So if I want that also to be equality, then the concavity of the logarithm has to be trivial. Okay, I mean, remember the log is strictly concave. So that becomes trivial if this probability distribution is a delta probability distribution. If this probability distribution is just concentrated on one point. Okay. So what does this tell me? So the second criterion is and this is a slightly more difficult criterion. So this says that, so I want this probability distribution. Okay, so for every I have this probability distribution, which I'm calling sigma. Well, yeah. So sorry, this probability distribution. So for every I have a probability distribution. Let's give a name to this. This is the probability distribution that I'll call, let us say Ri. Okay. So this probability distribution is supported over J. Right. So I is fixed, J is varied. So this probability distribution is supported over J. And I want this probability distribution to be the delta probability distribution. So it has to concentrate at one point. So in other words, the probability distribution II gives the entire mass of 1 to one particular J and the mass of 0 to the other J's. So to cut a long story short, what this means is that VI is equal to W Ji. Okay. And this was for the ith case. This has to be true for all I. So what is this saying? This is saying that there is a matching. There's a bijection between the eigenbasis of rho and the eigenbasis sigma. So if I take the ith eigenvector Vi, okay, it is exactly the same as the jith eigenvector Wi. Okay. So what is this telling me? This is telling me that rho and sigma actually have the same eigenbasis. I've just maybe interchange the order in which I list the eigenvectors, but they actually have the same eigenbasis. Okay. And so this is, so let me write it down. So this just says that is rho sigma have same eigenbasis. Is this part clear?
Yes.
Yeah.
Yeah.
I mean, this bijection condition actually says that this has to be the same eigenbasis.
Yeah.
Like V1 is equal to one particular W. Now V2 has to be equal to one particular W. It cannot be the earlier W. I mean, because V1 and V2 are orthogonal vectors. So this means that V1, let us say, is W3, V2 is W5, V3 is W1, something like that. Okay. So this mapping from I to Ji is a permutation of indices. So I have concluded that rho sigma have the same eigenbase. Any doubts? This is an important point. Okay. So they have the same eigenbases and then and what is the first condition telling me? That Pi is sigma ii. Now let us say I have relabeled the eigenvectors of sigma so that Vi is same as Wi. This is just saying that even the eigenvalue Pi is the same as what yeah. I mean the sigma ii now becomes an eigenvalue, the corresponding eigenvalue. So after showing that they're the same eigenbasis, I'm even showing that they're the same eigenvalues. So to cut the long story short, the operators are the same. Rho is equal to same. Okay. They're the same eigenbasis out here. And the earlier condition now says that the same eigenbasis, I mean, I'm writing them as matrices in the common eigenbasis, and this says that even the entries are the same. Okay. So any questions about this derivation? So I have proved property one that the quantum relative entropy is greater than or equal to 0. It is equal to 0 if and only if rho is equal to sigma. Okay. So let's go back. We have proved property one. Okay. Now let us prove property two. So the relative entropy is finite if and only if support of rho is contained support of sigma. Remember what support of a density matrix, or in general support of a Hermitian operator, or yeah. So support is basically the vector space spanned by the non-zero eigenvalues. So this is reminiscent of what you've seen classically, that d of p with respect to q is finite if and only if support of p is contained in support of q. So there the support of p was the subset of the sample space where the probabilities under p are positive, strictly positive. Okay, so this says that the sample points which get positive probability under p are also get positive probability under q. So that was the thing. And this is the exact quantum analog. But let us see how this is there. So we have done all the hard work already. Okay. So let's come to this expression. Okay. So now I want this quantity to be finite. Okay. So which basically means that this quantity should be finite. Okay. So pi log pi will always be finite. I mean, it is between 0 and 1, right? I mean, even if pi is 0, we know that this quantity is 0. So the only thing which can be potentially infinite is the second quantity, that is this. So let's write it down. Okay, so for all I want this quantity to be finite. So what does this mean? W, yeah, this is this W to Pi. Okay. Now, So let's look at this. So this, remember, I mean, for a fixed I, this is a probability distribution. In fact, I gave a name for this. So this was the, the probability distribution Ri, and this is the jth component of that. So this is Ri. So these are just probabilities. So this is a convex combination of some like positive real numbers. Okay. And if I want this convex combination to be finite, that means all these positive numbers here should be finite. So all I'm saying out here is that, okay, so log Qj is less than infinity if yeah. So sure, I mean the some Qj's could be zero, so log Qj could be infinite. That is allowed provided this probability distribution does not put any mass on that J. So for those J's, okay, lying in the support of this probability distribution Ri, log Qj should be less than infinity. In other words, Qj should be greater than zero. Okay, so this is say Qj. Okay, so let's stare at this. So is this part clear, Harry? This is how far we've come. That for every I, look at those J's such that this inner product between Wj and Vi is non-zero, and Qj should be strictly greater than zero for those J's. So this is true for every I. So you can take the union over all I's. So collect all those Qj's, okay, where Wj has a non-zero overlap with Vi. Okay? Any Vi, like Wj has a non-zero overlap with either V1 or V2 or V3. So, so collect all those J's such that Wj has a non-zero overlap with either V1 or V2 or V3 and so on. Okay, and then Qj for that J has to be greater than zero. Is it clear up to this point?
Yes.
Yeah, good. Okay, but what is this telling me? Okay, so so let us say, of course, yeah, and remember this whole thing is multiplied by pi's also. Okay, so of course, if pi is zero for some I, this quantity is taken to be zero. This quantity is also taken to be zero. So we don't bother about that. So basically, I'm only looking at those i's such that pi is greater than zero. So I'm only looking at the support of rho. Okay. So this quantity is saying that look at those eigenvectors wj which have a non-zero overlap with the support of uh, which have a non-zero overlap with the support of rho. Okay, so the VIs that come into question here are only the VIs in the support of rho. So look at those WJs that have a non-zero overlap with the support of rho. Okay, or if you look at the support of rho, it's a subspace after all. So look at only those WJs that have a non-zero projection onto the support of rho. And what I want is that the QJ for those guys has to be greater than zero. Okay. So this condition is equivalent to saying that if you look at the other way, look at the support of rho out here. Okay, so this support of rho has a non-zero projection to one of these j's. Okay, and Qj for that is greater than zero. In other words, the support of rho is contained in the support of sigma. So if I run over all these Qj's out here, I will basically span the support of rho. Okay. Another way to see this, maybe which is a little clearer, is I want to show support of rho is contained support of sigma, but this is again equivalent to saying saying like that here. Support. So orthogonal complement perpendicular contains the support sigma orthogonal, right? So this is just, I mean, geometrical property of vector space. So support rho is a vector space is contained in another vector space support sigma. This is equal to saying that the reverse containment holds for the orthogonal complements. So it's this thing for the orthogonal complements is easier to see. So let us look at what is support sigma orthogonal complement. Okay. So support sigma orthogonal complement is spanned by those j's such that qj is 0. But if qj is 0, that eigenvector wj cannot have a non-zero projection onto the support of rho, right, from here. So in other words, that vector wj, okay, yeah. So I started off with something in the orthogonal complement of support of sigma. So I'm looking at a j such that qj is 0. So that vector cannot have a non-zero projection onto support of rho. In other words, that vector lies in the support of rho complement. Okay, it only has a zero projection onto the support of rho. That's what I get from. So this is easier to see that support of sigma complement is contained in support of rho complement, which is equal to saying that support of rho is contained in support. Now is it absolutely clear?
Yeah.
Yeah. Yeah. Okay. So yeah. So let's pause for 2 minutes. So look at it. So this is slightly new material. Just go over it once and see if you can, if you have, I mean, any doubts out here. Digest it. Oops. There's no make it small or make it small.
Can you scroll up the main statement of the? Hello? Hello?
Okay, so let's continue. Yeah. Okay, good. Okay, so we have proved the two basic properties of relative entropy that I started with. We've shown that relative entropy is always non-negative. It is equal to 0 if and only if rho equal to sigma, exact analog of the classical case. And also we have a characterization of when the relative entropy is finite. It happens if and only if support of rho is contained in support of sigma. Again, an exact classical analog. So let's go ahead. Yeah. So what we have already seen from our classical study is that relative entropy is like a mother quantity. From that relative entropy, I can write down expressions for mutual information, conditional entropy, I mean, even good old entropy if you want, and yeah, so on and so forth. And the main thing to prove, the main non-trivial property of relative entropy, there was the data processing inequality. So that will be the same here. So there is a data processing inequality out here. So let's, but let me write down the derived quantities, all the derived quantities. Okay, so the rows. emphasize is the mother entropy.
These are not smooth quantities, right? These are
No,
like
these are not smooth quantities. So this is exactly like the Shannon entropy.
yeah.
So yeah, so I mean, by the end of December, we'll see the smooth analogs of those quantities also. Okay, and yeah, so what I'm hoping is, yeah. So anyway, I mean, by the end of this lecture, I'll tell you which is the hard thing to prove about relative entropy, and we'll do it in a very modern, beautiful way by the end of this course. Okay, so this is the mother entropic quantity. So, and let us see some properties. So first of all, the entropy of A under rho. Okay. So this is log of the dimension of A minus the entropy of rho A with respect to, so let us call it, so this is the uniform distribution over A. So this is defined to be the, so it's the classical distribution, also called completely mixed state. So it is a uniform probability distribution. So in terms of our matrix notation, it is the identity matrix divided by the dimension. So that's the uniform probability distribution. So exactly like classical, and you can, I mean, substitute the formula, and this is what will come out. So you can do it home as an exercise, but we right now we'll derive something a little more non-trivial. So similarly, let's go. So if I'm talking of entropy of A given B under rho. So now, of course, rho is a joint system on AB, right? So there is this underlying rho AB somewhere. So this is nothing but, again, it will be so rho AB, it's a joint density matrix. So note that I'm not assuming that rho AB is pure. Okay, so this is true in general. And this will be UA tensor rho B, exactly analogous to what we did last time. So rho AB is a joint density matrix. UA is this completely mixed state. Okay, the uniform probability distribution as I've written, identity on the system A divided by the dimension of A. Tensor rho B is the marginal density matrix on B. And again, I mean, maybe it's better you work out 2 directly, and from here, I mean, you will imply 1. Okay, so if the system B is a one-dimensional system, then entropy of A with respect to one-dimensional system is just the entropy of A, and that's it. So the only density matrix that can exist on a one-dimensional system is the scalar 1. Okay, it is the real number 1. So, and tensoring with the real number 1, I mean, really doesn't mean anything. So this rho AB is really rho A, and this is UA. So it's exactly this definition. Okay. What I'll sit and derive is the next quantity in line, which you can guess. So, okay. Before I do that, so of course, classically, I mean, we know what this conditional entropy is, but actually, strictly speaking, I have not defined conditional entropy in the quantum case. So, of course, you can take this as a definition, but you can check that this is equal to so maybe this is a little more interesting. Okay, So you can take one of them as the definition and the other as the theorem. So usually, I mean, in books, we will take the quantum condition entropy to be just this definition. This is the definition, and this is the theorem. So yeah, so basically, I mean, if you try to sit and prove this, let's say take this as the definition, and this is the theorem. And we already know that this quantity could be negative, right? We have seen the Arakili that this quantity could be negative. And sure enough, I mean, this quantity will also become negative. So really the exercise is to prove this. Okay. And now, of course, if B is the one-dimensional system, H of B will always be 0. Okay. And then AB is A. Okay. So all I'm showing is H of A given B is A. H. Okay. So proving 2 will be a similar exercise to proving 3. So what is 3? So I'm now going to define the mutual information between A and B under the joint state rho. So this is defined to be exactly as before. HA under rho plus entropy of the system B under rho minus entropy of the joint system under. This is the definition. And the theorem is, so you can guess. So tell me what will it be?
Rho A cross rho B.
Yeah. So it is the tensor product of the
Tensor
margin.
product of
Yeah.
margins.
So now let us prove. So and here this proof, you will see the power of the tensor product notation and all the identities. This is first of all definition. OAB. So let's explain this step. Okay. So this is because, so I know rho A tensor rho B is, this was the property of the Kronecker product of matrices. Yeah. Hope you recall that. Right? Do you recall this step?
Yes.
Yeah. So I have this, and now, okay. So now if I take logarithm, okay. So remember that the eigenvalues, in fact, even the eigenvectors. What are the eigenvectors of rho A tensor rho B? take the eigenbasis of rho A, take the eigenbasis of rho B, and take the tensor basis. So the tensor basis is the eigenbasis of rho A tensor rho B, and the eigenvalues are the pairwise multiplications of an eigenvalue of rho A times an eigenvalue of rho B. And now if I take logarithm, I know the eigenbasis of rho A tensor rho B, I know the eigenvalue. So if I take the logarithm will become a sum. Okay, so it will be log of an eigenvalue of rho A plus log of another eigenvalue of rho A. So I'll have to take all possible pairs and then take the sum of the logarithms for each. So now I claim that this expression is nothing but now why is this? Oh, where did it insert the page? I have to reorder the page. Okay. Okay. So what is this? So there's nothing mysterious about this. Right? This is the rho A and rho B. So this will be some pi qj, right? So this is how the eigenvalues will look like. Okay. Now, and now if I take log, so then I'll get same thing, but it will become log pi plus log qj. Yes. But what is the log of rho A tensor identity B? So there, the corresponding entry here will just be log pi, right? So this is a diagonal entry corresponding to the ith eigenvector of rho and the jth eigenvector of sigma. Okay, and same entry ith eigenvector of rho and the jth eigenvector of identity. But fine. So the eigenbasis that I'll take for the identity on B is nothing but the eigenbasis of rho B, right? And similarly, in this expression, when I take the eigenbasis of the identity on A, it is nothing but the eigenbasis of rho A. So it's the same entry, okay? But now, of course, the corresponding eigenvalue was just pi here. So pi is coming from rho A and 1 is coming from identity of B. So it's just log of pi. And now you can see that the same entry log of identity A tensor rho B, same thing. So here I get log of qj. Okay. At the same position. The same position. So of course now when I add these two guys up, I get this. Is that clear?
Yeah.
Yeah. Yeah. So this is one quickest way to see it in terms of eigenbasis. There are a little more abstract ways to see it. So one thing is the logarithm, even in the matrix world, is the inverse. I mean the functional inverse of the exponential function. Okay. So again, I mean, how do you define the exponent of a matrix? Go to its eigenbasis and then exponentiate the eigenvalues. Keep the eigenvalues. So viewed this way, the logarithm is the function inverse of the exponential. Okay. And it's a nice exercise to show that if matrices M and N commute, then let me write that. Oh, sorry, let me write that. Okay.
For any general matrix, the exponent of a matrix is the like the Taylor series expansion of
Correct,
the
correct. That's how you can define it in general. Yeah, very good. So
yeah, yeah.
e to the m, actually you can define it identity plus m by 1 factorial m squared by
Yeah,
2 factorial. Yeah, yeah. So you've seen this, right?
yeah.
Yeah. And you can show that this converges, okay, irrespective of the matrix. But if now M is a diagonalizable matrix, let us say M is a Hermitian matrix, okay, or maybe more generally, M is a normal matrix. Okay. So if it is diagonalizable, just evaluate this expression in the eigenbasis of M, okay, in the diagonal basis of M, okay, and then this just amounts to exponentiating the diagonal elements individually, but the diagonal elements are now the eigenvalues. So, for example, if M is a Hermitian matrix, this definition agrees with the definition I told you. Go to the eigenbasis and exponentiate the eigenvalues. Okay. The point is, e to the power n actually can be defined for every matrix, but you cannot define log m for every matrix. But if you, but we are only restricting ourselves to Hermitian matrices. I mean, the only expressions will be either rho or rho minus sigma if you're looking at the L1 distance between them. So our world is mostly limited to Hermitian matrices for now. So for Hermitian matrices, both exponentiation and logarithm make sense, and you can define it in terms of the eigenbasis and eigenvalue. Okay. And the definition of the exponentiation in terms of eigenbasis agrees with the more general definition in terms of this series. But this series is important because from this series you can now conclude that if m commutes with n, okay, so I mean by that I mean like mn equal to nn. If this happens, then you can prove that e to the m plus n is equal to e to the m times e to the n. And again, the order here will not matter because m and n commute. So this is also e to the n times e to the n. Right? This you also you may have probably seen if you've seen this
Yeah.
Taylor expression. Okay? And in general, it's not true. If m does not commute at n, then this actually will not be true. But in our case, what I'm telling you is just this. So I mean, so my e to the n that I'm taking will be rho a. That's identity of B, and e to the n will be identity of A, that's rho. Note that these two matrices commute. Okay, so it's expected that even m and n, which are the logarithms, will commute. But in particular, what do I know? I know that e to the n times e to the n. So this is rho A tensor rho B. So but this is equal to e to the m plus n, right? But now this m is the mysterious logarithm of rho a. Okay, suppose I didn't know the explicit thing. So what does this say? This says that log rho a tensor identity b, right? So this is n, and n is the other one, log identity a, rho b. So basically, what I've proved is that m plus n is equal to log of rho n, right? That is exactly what this expression is saying. Compare e to the power m plus n on the extreme left and this on the right. So this says that n plus n is the logarithm of rho a tensor rho b. Is this now clear?
Yes.
Yeah. So this is another way of doing it. So there was an explicit way, but there is also the more sophisticated. Good to know. Okay. So now coming back to our mutual information business. So I've shown that. Oh, so I want to show this. So yeah. So I've shown that d of rho a, rho a b with respect to rho a, that's rho b is equal to raise rho a b log rho a b minus log. Okay, so let me write it down. Now I'll do another quick simplification. Put the brackets. Okay, but this I claim is equal to okay. Next step. So I'm claiming that log of rho A tensor identity B, rho A tensor identity B is log rho A. So apply the logarithm only to rho A and tensor it with the identity matrix and similarly. So again, this is clear from the explicit expression that we wrote out here, right? So the right. So what was log of rho A tensor identity B? Then in the ijth entry, I have log pi, right? But this is true for every j. For every j, okay, let's fix I, but let j vary. I have log pi, log pi, log pi, log pi everywhere. So this is nothing but take logarithm of rho itself. So that will only have one log pi and tensor it with the identity on B, okay, which will repeat the log pi across. Is that description clear?
Yeah.
Yeah. So one thing is from the explicit thing. And I mean, since you know this more sophisticated way, you can even derive it from the more sophisticated way. Like from a similar analysis, you can show that log of rho A tensor identity is log rho A. Okay, evaluate the logarithm on rho A itself and then tensor the identity. So you can also show it by connecting it to the exponential. Yeah, I mean, you can exponentiate one and see what you get. Okay, right? So I mean, you can exponentiate this and see what you get. You will actually get rho A tensor identity. Okay, so after I've done, let us see what do I get out here. Okay, so let us evaluate this. one of these quantities. So let us see what this expression looks like. Trace of rho AB minus log rho A tensor identity. Let's see what this looks like. So now we will see another property of the partial trace. So this is the same as trace of, take the partial trace of rho A. So I have the identity B out here. If I want to remove the identity B, I have to take the, I have to trace out the system B from this matrix. So this is this B, rho AB times. So now the system B is gone, and I only have matrices over the system B. So I hope you remember this expression. So this was a property of the partial trace. Okay, so the expression to jog your memory was this trace of some matrix MAB times NA tensor identity B. So this is equal to trace. So I trace out the system B from M. And this N is that. So do you remember this? So this we discussed some lectures ago when we were doing the partial trace. And in fact, I had, I mean, there was a discussion, Shannon, and I would remark that if you want to define the partial trace abstractly, you can use this to define it. I mean, it's the adjoint of the inner product on matrices, a certain operation, and the adjoint is computed over the inner product matrix. So, I mean, that was the fancy way of writing this, but this can also be taken as a definition of partial trace. But anyway, I mean, we have defined partial trace with the basis dependent definition, explicit definition, and then we saw that this is true. Do you recall this expression?
Yeah.
Yeah. So that's exactly what I've done. Okay. So now we are done, really speaking. So what is this? This is equal to minus trace rho A. By definition, this is rho A, and this is log rho A. Okay. So this is our good old entropy of. So what have we done? So we're almost there. Okay. So let me show you. So, oh, not there. So B of. So this is so minus is what it shows is rho A log rho A minus is from these three terms. First term is this trace of rho AB log rho AB. This is trace of rho A log rho A. This is trace of rho B log rho B. Right? And that's it. So by definition, this is finally. So this of course was defined to be the mutual information. So any questions?
So
So if you,
the essence
yeah,
of this proof is the writing that writing the trace in the other form.
yeah. So I mean, one clever step was this, that split up the logarithm out here.
Yeah, yeah.
Yeah, then observe that, I mean, the log can be moved inside, the identity comes out. Okay. And the moment this happens, then I use this property of the partial trace. So trace of row AB, log row A, tensor the identity outside. So that means I can just drop the system A, take the partial trace of it, drop the system A. And I get this. So it is quite instructive at this point that you go back to the classical proof of the same thing. Okay, that D of PAB with respect to PA times PD. So that will also boil down to this expression. So look through the steps of the proof and see how they're exactly analogous to this proof. All the steps are the same, except that we need more sophisticated notation and the accompanying machinery to justify those steps. But it's actually the same proof. Okay, it's very instructive proof. I mean, write down the two proofs side by side, okay, and then just compare like which step corresponds to what. Okay. So already this is telling us something fantastic. So for example, I mean, if you look at this formula for the mutual information, right? So I mean, just from this HA plus HB minus HAB. So you can write the standard expressions that we are all familiar with in classical, that this is the same as HA minus H of A given B, where the conditional entropy is defined in terms of the Shannon entropy only by subtraction. Same as HB right? So both these expressions are come from here. Right? The same thing that's written in two different ways. So all these expressions are there, but the worrisome part is that like uh, so what do we know? I mean, we know that this quantity could actually be negative. Okay,
Yeah.
the conditional entropy could be negative, and then I mean this thing can look weird. So one particular thing you can already see is that classically I know that the mutual information between A and B is upper bounded by the entropy of A or the entropy of B. So take whichever is smaller. But here, if this quantity is negative, then this is larger than the entropy of it. So the question is, so sure, the quantum mutual information, if I want to upper bound the quantum mutual information, so I mean, it can indeed be greater than the entropy of it, but it cannot be too much greater. You can see that it is less than 2HA. Okay, and then of course also 2HP, like the same thing. So how do you get it? This you'll get from the Araki Lie. Okay, so sure, H of A given B can be negative, but H of A given B, okay, so this is HAB minus HB. But the Araki Lie says that this is always greater than minus H. Okay. So,
Yeah.
so if you do that, you get to H. So far so good, but given this weirdness of quantum, okay, and the fact that conditional entropies can be negative, I mean, classically no entropies can be negative. You may start worrying whether the mutual information turns out to be negative or not. So conditional entropy can be negative, but what about mutual information? So this expression, the theorem that mutual information is actually relative entropy assures us that mutual information is still positive.
Yeah.
So this is a more non-trivial fact out here. And I mean, classically, I mean, without the relative entropy machine, you could have said that, oh, this is HA minus H of A given B, but H of A given B is always less than H of A. So the so I'm done. Okay. Then the mutual information is positive. Like often that's how it's done in books. But in quantum, a priori you cannot say that conditioning decreases the entropy. Okay, because of all this weirdness. So the only proof that we have that condition decreases the entropy. It is true, of course, condition decreases the entropy. So even though conditional entropy is negative, weird things happen. Conditioning always decreases the entropy, and that is because of this. To show that HA is larger than H of A given B, the only proof we have is to show that this difference is the mutual information. The mutual information is greater than or equal to 0. It's greater than or equal to 0 because mutual information is a relative. Okay. So even though there is quantum weirdness in entropies, okay, and entangled states have very strange conditional entropies, still the mutual information picture is not that weird. Mutual information is positive exactly as in the classical case. This is one non-trivial fact. Okay. And so in fact, if you write down, so it already gives a consequence which is, I mean, more non-trivial in quantum than classical. This says that this implies, in fact, is equivalent to saying that H of A given B okay.
Which quantity can be negative? H of A given B.
Yeah, this can be negative. Yeah,
Yeah.
yeah, this is always positive. Again, because yeah, so which you have seen it. I mean, this is just the Shannon entropy of its probability distribution with eigenvalue. So this is always positive. Okay, this could be negative, but I mean, without this machinery, like sure it can be negative, but it can also be positive. So I mean, could it shoot up above this? Okay, especially I mean, you may worry with entangled states. Who knows? There's with a different entangled state, something may shoot up. So the answer is no, it cannot shoot up, and that's because of this. But already there are new consequences that the mutual information can be larger than H of A. So in fact, if you take the EPR state and look at the mutual information, it will be 2. So entropy of A is 1 there, but the mutual information is 2. So very, very different thing. And a more sophisticated understanding will say that, yes, the mutual information is 2, out of which 1 is classical. I mean, that is like having 2 correlated random bits. So one bit of the mutual information is this classical correlation. The other bit of the mutual information is purely quantum. And they call it the entanglement bit, E bit. So indeed, I mean, you can saturate this bound. These kinds of things happen, but still there's some sanity that this is greater than or equal to 0, and this is coming from the mutual information. What is still not clear is what happens with further conditions. So we'll stop here. So this is a food for thought, and we will address it in a few lectures. And this is the really non-trivial food for thought. Okay. So is so what happens with further condition? This is the question. Is it less than H? So classically, of course, I mean, we know how to prove this. I mean, we will just fix B to something and then we'll invoke the earlier one. But quantumly, you cannot fix the B to something. Okay. So you have to go back to scratch and you can open this out in terms of entropies and you'll see that you get an expression out. We'll do it next time. And that expression is more complicated than this mutual information. So, I mean, you'll see it is the expression you get from the conditional mutual information, which again is very familiar classically. And then the question comes is the conditional mutual information always positive? Okay. And classically, as I said, the answer is easy. You just fix B to some sample point, evaluate it, and then take an average over B. Quantumly, you cannot do that. So it was open for a long time Well, long time means, I mean, people were not really asking those questions, but as you can see, whatever we have done so far, that machine is not enough to tell us whether conditional mutual information is positive. So positivity of mutual information we have proved by connecting to relative entropy, but that does not seem to imply positivity of conditional mutual information. So that is a food for thought. Is this true? But anyway, the answer is it is true. Okay, and this will lead to, I mean, a highly non-trivial behavior of quantum entropies, and eventually we will relate all this to, I mean, we have a big hammer, which I've still not stated, that is the data processing inequality. So we'll state what is data processing inequality for the relative entropy. And if you assume data processing inequality of relative entropy, you can answer this in the affirmative. You can say that you can also prove the Araki-Leib inequality from there. I mean, it's again related to this question, the Araki-Leib inequality. We'll see how. Okay, so a lot of interesting things are related to this question. So that's why in the literature, people have given it a special name. So you can call this subadditivity of entropy. This the fact that mutual information is greater than 0, you can say that entropy is subadditive. Okay, h of AB is less than or equal to h of A plus h of B. So then, but if you frame the analogous question here, you get something involving ABC. So that's called a strong subadditivity of entropy. And that is a much more difficult thing to prove. Okay, and in fact, the only proofs used sophisticated matrix analysis till very recent. And in this course, we'll see a very recent proof. And the amazing thing is that, so we'll take a modern view, we'll tie all of this to the data processing property of relative entropy. Okay. And we'll see that, I mean, if we assume that strong subadditivity, like further conditioning, all these questions can be answered in the affirmative. Araki-Leib inequality can be proved. Okay, so it only remains to prove data processing inequality for relative entropy. And as I said, till recently, I mean, the only proofs of it were highly sophisticated. But now we'll see how information theory, how one-shot information theory allows us to prove. So we will, instead of answering it directly, like classically we could have answered it directly, but instead of answering it directly, we'll go to one-shot smooth entropies. So, and then we'll prove a data processing inequality there. Then we'll prove asymptotic equipartition there, exactly as we did. And from there, we'll deduce the data processing inequality of Shannon. So it will be a long process. The rest of the course will eventually lead up to that. Okay, but that will be an elementary thing, and it will show you the power of one-shot techniques. And it has completely replaced a big matrix analytic part of the literature by like simple information theory techniques. Okay, any further questions? Okay, so we'll stop and see you on Thursday.